we know what does it mean, the cross product geometrically, right? If you're given a t vectors, u and v, the cross product of the u and v is going to be a vector which is going to be perpendicular to both of the vectors at the same time, right? It's going to be u cross product v. Okay, so now let's talk about more geometric implications of the cross product. So the first exercise which we are going to do is we are going to give a vector vu with the components u1, u2, and u3. And I would like to find the cross product of this vector u to itself. Okay? So this is going to be, do you remember how to write this down? So we need to write I, j, k, right? Then we need to do u1, u2, u3. Then we need to put u1, u2, u3, right? Okay, so if I find the determinant of this three-dimensional matrix, it's going to be I multiplied to the u1, u3 minus u1, u3, right? Minus j multiplied to u1, okay, it's u2, right? 2. So if I multiply this to the minus j, it's going to be u1, u3 minus u1, u3 plus k multiplied to u1, u2 minus u1, u2. Okay? So all the three components is going to be equal to the 0. Okay? This is going to be not a constant 0. This is going to be a vector whose components are 0, 0, and 0. Okay? It means that this is going to be a 0 vector, right? Okay? It's important. So when you multiply two perpendicular vectors as a dot product, you're going to have a scalar 0. Okay? And if you multiply two vectors, which are the same, for example, you're going to have a vector 0. Okay? So what kind of conclusion you see from here? So you have one vector here, you have another vector here on the top of this. So we have learned yesterday that if you have a vector here, you can put this vector to any place, right? Do you remember? For example, this vector is v, okay? Or let's talk about the position vectors first of all. So we are going to talk about the position vectors, right? Do you remember what does it mean, the position vectors? The vectors should start from the origin always, okay? So let's do this in the 2D. It's easier. So let's say you have the vector here, okay? And let's say vector omega is a vector which is parallel to the vector here. How I need to draw this? How I need to draw a parallel vector to the u? If both of the vectors should be position vectors, right? So previously we've learned that two vectors in a school, right? Especially two vectors, u and v, are going to be called the parallel lines or parallel vectors if they never intersect, right? So this is going to be a wrong definition for us because if we're going to move the vector v to the origin, they're going to interact infinitely many times, right? So here for the vectors, especially for the position vectors, we're going to define the parallel vectors in the following way. If the two vectors, u and v, are parallel, then they are on the top of the others. Okay? So the second vector which is parallel to the u should be on the top of the u. Do you understand this? Right? Because all the vectors should start from the origin. Right? And there is the only way to draw the parallel vectors. Both of the vectors should be on the same line, actually. Okay? So what does it mean, this exercise, or this exercise, what does it mean? So u, and another vector u, which is on the top of this u, and the cross product is equal to the 0 vector, right? And at the same time, if you would get the v vector, for example here, you know what I mean? If you get v vector, is it possible to get a v vector from the u? How to get the vector v from the u? By making it longer, by scaling this, right? By multiplying some constant to the u, you can obtain the v, right? Actually, u and v are very similar, right? So you can obtain the second vector v by just multiplying the u to some constant, right? And when we say that the u cross product u is equal to the 0, it also means that u multiplied to the v is equal to the 0 vector when u and v are parallel. Okay? Let us write this down. So let u and v, so u and v are called parallel, if u can be obtained by multiplying the v to some constant. Okay? For example, 1, 2, 3 is the vector u, and v is going to be 2, 4, and x, maybe. Okay? So which value of the x I need to choose so that u and v becomes parallel? 6. Okay. So if I would set x to be equal to the 6, then u and v becomes parallel, right? Why? Because if you multiply the u to the 2, you can obtain the v. Do you understand this? So now this is we're going to define the vectors, two parallel vectors, differently, right? So geometrically, they are going to interact infinitely many times. At the school, we define them as two lines which never interact, right? And now they're going to interact infinitely many times. Okay? So the two vectors are parallel if you can obtain one of the vectors by multiplying the second to some constant. Okay? And if we're given two parallel vectors, if we're given u and v in 3D are parallel, then u cross v is equal to the 0 vector. Okay? If we're given the t vectors, which are parallel, then u cross v is equal to the 0. So please note that it works in both directions. Okay? So when we say the both direction, it means that if the u and v are parallel, then the cross product is equal to the 0 vector. And if the cross product of the t vectors are equal to the 0 vector, this is the case when t vectors are parallel. Okay? You know what does it mean? It works in this direction and the vice versa direction. Okay? So at the same time, so let's define. So do you remember what was the parallelogram? Right? So let's say this parallelogram is defined by the two vectors and the angle between them. Okay? So this is going to be a vector u, and this is going to be vector v, and this is the angle between them. Okay? So do you remember how to find the area of the parallelogram? You need to multiply the height to the base, right? So this is very similar to the area of the triangle, right? So on the triangles, you need to multiply the height as the base and divide this as a 2. For the parallelograms, right, it is going to be, it's a twice triangle, right, actually. So you can find the area of the triangle by multiplying the height to the base, right? And since this is the twice triangle, the area of the parallelogram, it becomes height multiplied to the base, right? Okay, so if you're given the two vectors u and v, how to find the height? The height is going to be equal to the u norm multiplied to the sine of alpha, right? And the area of this triangle, of this parallelogram, is equal to the norm of the v multiplied to the norm of the u multiplied to the sine of alpha. Okay? And it appears this is equal to the norm of the u cross v. V cross u, or u cross v. It doesn't matter here. When you find a norm, it's going to be the same. Okay? So please note that u cross v is not equal to the v cross u. Okay? So u cross v is not equal to v cross u. Okay? It matters when you multiply the first one to the second or second to the first. Okay? But they are very similar, actually. So they are going to have the same vector, but the directions will be opposite. Okay? So that is why when you take the norms, they're going to be the same. Okay? So here, you can write this as a u cross v or v cross u. It is going to be the same. Good? So for example, another geometric application of the cross product is going to be the area of the parallelogram. Okay? So let's do an exercise. So find the area of the triangle was the following vertices. So P is given was the 1, 4, 6. Q is given was the -2, 5, and -1. And R is given was the components 1, -1, and 1. Okay? So basically, you're given a triangle with the vertices P, Q, and R. Okay? So you need to find its area. So what is saying how we can find the area of this triangle? Actually, we know that we can easily make this triangle or make the parallelogram using these two vectors, right? So if we would be given this vector and this vector, we could make the parallelogram, right? Like this. And we know how to find the area of the parallelogram, right? And this area, the area of this triangle, is going to be just a half of the area of the parallelogram, right? So the only thing which we need to do is we need to define this vector and this vector, okay? So the vector PQ as a position vector, PQ vector, right, can be found by subtracting the initial point from the ending point, okay? So we need to write the ending point. It's going to be -2, 5, and -1. Minus P, it's going to be 1, 4, and 6, okay? This is going to be a position vector, okay? Basically, this is the vector. We can define the vectors with the 2 points, starting point P and ending point Q, or we can define the points with only 1 point when we move the vector to the origin of the coordinate system, okay? So we can build the position vector from this vector by subtracting the initial point from the ending point, okay? So if you subtract this, what you get? -3, 1, and -7, okay? This is going to be our first vector. Let's say this is U, okay? And our second vector, V, is equal to the PR vector, right? And we can obtain this by subtracting the initial point P from the R, okay? It's going to be 1, -1, 1, minus the P, it's going to be 1, 4, and 6. If you subtract this, it's going to be 0, -5, and -5. Do you agree? Okay, so now in order to find the area of the triangle, we need to multiply the U to the V as a cross product, right? And find its norm. This is going to be the area of the parallelogram obtained by these 2 vectors, right? If you divide this to the 2, this is going to be exactly the area of the triangle. Okay? So let's find the cross product first, then find the norm of this vector, then divide this to the 2. Okay? So what is the cross product of the U to the V? So we can do this using the matrices. We need to build a matrix I, J, K on the first row. On the second row, we need to write down the components of the U vector, right? It's going to be -3, 1, -7. On the third row, we're going to write down the components of the second vector. It's going to be 0, -5, -5, okay? So the I component of this vector is going to be equal to the determinant of the 1, -7, -5, -5, right? The J component is going to be equal to the -3, -7, 0, -5. And the K component is going to be equal to the -3, 1, 0, -5. Okay? It's going to be I is multiplied to the -5 plus 35, right? It's going to be equal to the 30. Minus J multiplied to the -15, right? And K multiplied to -15, right? This is going to be a vector with the components 30, 15, and -15. Okay? So the area of the triangle is going to be equal to the norm of this vector, 30, 15, and 15, divided to the 2. Okay? Oops, sorry. So here we have 40. I have a mistake here, 40. Right, because the determinant of this matrix is going to be equal to, here is -5 as well, right? It's going to be -5 minus 35, sorry. It is going to be equal to this one. This can be found by taking the square root of this, right? It's going to be square root of 40 in a square, plus 15 in a square, plus 15 in a square, divided to the t, and you can easily calculate this using the calculators, right? This is going to be actually 5 multiplied to the square root of 80t. Okay? So there is one more formula which we used before here. So this formula tells me that theorem. So let we're given the t vectors with the non-zero angle between them. Let u and v are t vectors in R3, okay? And have the angle alpha between them, okay? Between them. And this alpha is between 0 and pi. Then the following formula works. So u multiplied to the v as a cross product in a norm is going to be equal to the norm of the u multiplied to the norm of the v multiplied to the sine of alpha. Actually, we used this formula before, right? Okay. And one more amplification of the cross product is when we would like to find the volumes, okay? So let's say we're given a 3 vectors, omega, u, and v. If you're given the 3 vectors, is it possible to obtain the parallelepiped from this? Parallelepiped. Do you remember what was this? So you need to make this kind of object, right? Okay? So if the parallelepiped is given with the 3 vectors u, v, and omega, then its volume can be found using the vector operations. So the volume of this parallelepiped is going to be equal to the u multiplied to the v cross product is omega, then its norm. Okay? So let's do an example quickly.